Hello, students. We are jumping into chapter 14. It's our last chapter, and as you can see here, we've got 3 whole sections to cover. Now, I know that's not a lot compared to some of the other sections, but this section is definitely going to be, this chapter is going to be a little bit more um, visual. Some of the other ones are a little bit more abstract, so you have to do more thinking, but this one's definitely going to be a little bit more visual. And that's because we are doing things with transforming shapes. So think about kind of physically moving a shape. And we'll take a look at a couple pieces in 14.1 and 14.2 that deal with how do I move a shape but keep the shape kind of the same. The areas are the same, the lengths are the same. And then in 14.3, we'll talk about how can I move a shape or make some of these changes where maybe the size does change. And we call that a dilation. So it starts with a wonderful problem about identical umbrellas. Love it. There are 2 apparently that are identical. They can be rotated but not flipped. And what they're saying here is that they're trying to show this as a way of linking to the 2 ideas. Rotations are one of the transformations that we're going to make sure we study in this section. So let's jump to the next page. We'll talk a little bit about Common Core pieces. So they talk about here Common Core lists verify experimentally the properties of rotations, reflections, and translations. Lines are taken to lines, segments to segments, angles to angles of the same measure, and parallel lines to parallel lines. Excuse me. Now, that is the Common Core for grade 8, but I will tell you that a lot of these pieces are integrated sooner. You'll see shapes being moved as early as the K through 5 grades. It's just where are you experimentally verifying the properties? That's when we get to grade 8. All right. So let's take a look. A couple pieces. What we're going to have is linking back to something from the Math 105, which is a one-to-one correspondence. And what we're thinking of, though, is as we move something, we'll think of kind of one point to one point, kind of how did it move? And so we will have this idea of almost like a function, but something that moves it. That thing is called a transformation. And the original we had becomes the image. Okay. Now, key piece here for most of the transformations we're going to cover is that they preserve distance. And they use the word isometry. Now, if you're in athletics or anything like that, you might have heard of isometrics, and it's very similar. An isometric exercise is one where you, like instead of like moving your arm up and down or moving your, doing a bicep curl, notice that things are not staying the same. You're moving angles, you're moving all this. Isometrics are where maybe you keep your leg in exactly the same place, but you just pull different muscle groups. You like squeeze your muscle tight so you contract it, but without moving the rest of the components. And if you think about that, that means is basically we're keeping things the same measure. And isometry comes from, and so I looked this up here. Where was it up here? Here we go. Comes from 2 words. Ancient Greek, isos, meaning equal. And again, we've seen that with isosceles, right? Where we have the 2 legs that are equal. And metron or metric, which means measure. And so what we have here is we're going to be doing things that keep the same measurements. Okay, what does that mean? Distances are going to be the same. Angles are going to be the same. All of those are going to be exactly the same. The orientation may not be the same, but we'll see how to work with that. Let's jump in. And I will also, we'll do probably GeoGebra is probably going to be the tool I use for a lot of these pieces, so you can kind of visualize them. However, big pieces, the first big one that we learn about is a translation. A translation is often called a slide. So what we have is we have a starting point, which is like the original, and you'll see sometimes they call it the pre-image. Image is like the end, pre-image then would be the beginning. And so that is denoted by some type of arrow. And it's a little hard to see, I think, even in the book, because what they're trying to show is action. And action is a challenging thing to show in a static textbook. So right here, there is an arrow with like a starting point and an ending point. Now, what that is showing is it's showing the direction and the magnitude. How far did I slide? So when you look at the image above, this is why it's a little challenging. I'm going to use this tool that allows me to just kind of move something. So notice I'm keeping the exact same length and everything that I had at the beginning. All I'm going to do is move it around. When I take this slide arrow up, then I say if I started at point A, where do I end? So as you see over here, A would be my pre-image or my original, and that arrow would then take me over here to A prime. And you can come down here to B and do the same thing. Okay, well, where does B move? Well, B moves to B prime because it uses that exact same arrow. So I can't twist the arrow. I can't elongate the arrow. It's everything I need. But what that means is when you get to the end, you have A prime and B prime, and they will be the same. Oops, clicked on the bottom part of the box. I didn't mean to. They will be the same distance apart. And since they're the same distance apart the whole way down, you've basically created a parallelogram. From what we've seen in the previous chapters, parallelograms have equal sides. The opposite sides have to be the same length. So A prime, B prime is going to be the same length as AB. All we did is slid that segment. So let me go ahead and grab a line segment tool here to just kind of illustrate that. If this is my original segment, AB, you can see that sitting right here. And I wonder, let me see if I can make that larger. Doesn't look like it. So maybe I'll put one right over the top of it. Okay, so there's AB, right? There's my segment. And so all I'm going to do is take that exact segment and I'm just going to slide it over till it's sitting right on its new destination. They've got an image here. I think the reason they're trying to use the actual slide is because that's what a kid did. He went down the slide, so that'll stick in your mind. But notice there's a starting point for the child's head and then a direction. And that is the idea of a translation. Translation, also known as a slide. Okay. So here's official definition. Translation is a slide arrow. So again, even though it says MN, what we're saying is that the translation moves everything like M moves to N. Okay, so we have that kind of image. All right. What else do we have here? Oh, so this is kind of how you can do this. They say using tracing paper. We could use patty paper as well. So what you can do is you can take the patty paper, kind of set it over the top, and then you kind of move the shape. And you have to have your slide arrow and your slide line on the page. So I have those written down, say, here's the direction I want to move it in. And then when you do, you will create an image. So you can actually see the piece kind of sliding across. And if you'd like to illustrate that, let me see if I'll do my best to do that. So here's A to B to C. So there's kind of the outline, right? And then what we're doing is we're going to take all of those and we're just going to move them, sliding it over to the right. And that is it's kind of an action. So there we go. Now you will create, again, because you're creating parallelograms, you have parallel lines. So you'll notice A to A prime is parallel to B prime is parallel to C prime, because all the lines that you just made are going to be parallel. And they're all based on that line called MN. Let me clear my drawings. Okay, so how do we construct translations on a geoboard? So notice it says, find the image of AB under the translation from X to X prime. So this X to X prime gives me an arrow. So if you take a look at how it slides down to and right to, that's the motion. So as you do this, you could come in and say, okay, so I go down to right to. So point A right here is going to move just like X moved to X prime, and it's going to move to here. Okay, and let's see. I think I have this other tool. I'm going to try this one. Let me try that again. So it moves just like that. Okay, so that's where it's going to move. And B is going to move exactly kind of in the same way. This is called the vanishing pen. I think it's kind of cool. Okay. So when you're done, you'll have a new segment AB, and you simply draw segment AB in, and it's right here, and then label it. Ooh, I was still on vanishing pen. So we'll have AB, and it's located right here. I got to go back to line segment tool. Clearly, I cannot draw a straight. Oh, wait, let me use my other little digital tool. Maybe I can do it. Okay, there we go. And then you do want to label it because the orientation matters. And so when you come in here, then just label this one as like an A prime. That's good. And up here would be a B prime. And that is how you can do a translation. So you just slid the segment AB kind of down and to the left. And there it is. Same type of thing. Can you do this in Cartesian coordinate systems? Yes, you can. And again, the link to the Common Core describing the effect of dilations translations on two-dimensional figures using coordinates. The using coordinates part tends to be why it gets bumped up to grade 8. What we just did with graph paper can obviously be done a lot earlier, but coordinates like this are going to act different. However, I want you to see it's the same concept. Start, we're moving in the direction from O to O prime. So here's O prime. So I'm going to go down to right 5. So the Y coordinate that I started with has to go, the X coordinate I start with has to go right 5. So that's why I do an add 5. The Y coordinate has to go down 2. So that's why you'll notice it goes down 2. So you take this original and you come over here and that's the result. Okay. So it really is just moving points and in a sense, just kind of adding things. So you'd start, if we started with this -2, 6. So I'll start with this point right here. And we'd say, okay, take -2 and add 5. Well, -2 plus 5 gives me 3. And then I take 6 and I subtract 2. 6 minus 2 is 4. So my new point becomes 3, 4. And that's what you see listed right here. Okay. So as they write it out, I think it's kind of nice. It's not bad. The XY goes to X plus 5, Y minus 2. So it tells you the type of translation symbolically. It says move like this. And this depiction is really telling you how did O move to O prime. All right. So what you'll see is it is written this way. A translation is a function of the plane such that the point with the coordinates xy is now x plus a, y plus b, where a and b are real numbers. So find the coordinates of the vertices this under the translations that they give you. So you'll notice they will give you a translation like this. xy becomes x minus 2, y minus 4. Well, if you're doing a problem like this, all you're going to do is say, okay, x values go down by 2. So see this B coordinate right up here? Its x value goes down by 2. So it's now sitting here. This A coordinate is now sitting here. This C coordinate is now sitting here. D coordinate is now sitting here. So that's the X portion. Now the Y portion says take those moved components and take all of them up 4. 1, 2, 3, 4. Got it. Okay. 1, 2, 3, 4. Got it. 1, 2, 3, 4. Got. Oh, it's right on top of that other point. And then 1, 2, 3, 4. Okay. And then you can just draw in your final shape. And there it is. That's what your shape did. It moved up and to the left. Let's see here. Translation determined by this slider. Okay, so if they give you a slide arrow, you can create your own translation. So I'm not going to go through those because I think those are going to be pretty quick. Okay, let's jump in. All right. I think these are Frise patterns. Let me see here. Am I saying that right? Frise? That's how one of my teachers said it. How do you pronounce this word? Freeze. They just call it freeze patterns. Ah, he said it was Frise. Well, learn every time. Always good to learn something new. Now, basically what they're saying is if you look at things that you see out in the world, whether it's tiling patterns on the ground, maybe it's wallpaper on the wall, but you will see basically a similar idea, whatever this looks like, is copied and basically just creating a new translation. We're just sliding something across. Okay. So number one, translation. Number two, rotation. Now, rotation obviously is exactly what it says. It's just a turn, it's a twist. But in order to know how it's twisting, we need to know a few things. First, we need to know where does it start, which is known as the turn center. Okay. And then we need to know the angle that it's going. And we also need to know which direction is that angle, because you could go 30 degrees clockwise or 30 degrees counterclockwise. So what we're going to do is we're going to say that a positive turn is counterclockwise and a negative turn is clockwise. So if you watch, if I did this kind of a turn, like this direction, that's clockwise. So that would be a negative number. So if I moved 90 degrees, then it would be negative 90 degrees is what I would write down. All right. So the image over here isn't bad. I wish they had done a different color on the side. And that's because this shape that we have at the end, this ABC that I'll kind of put in blue here, that is the image. So again, it's kind of hard to see what's happening here. You had a pre-image, which is the same triangle. Then I turned it 150 degrees clockwise, which would be negative 150. So that turn angle is 150, but when we write it down, we would actually write down negative 150. Okay. So there we go. Here's a school book, Understanding Translations. So they give some examples. Again, this one with the coordinate systems would be grade 8. And if you wanted to construct a rotation by tracing paper, what you have to do is you put your angle down for your rotation angle, your center, and kind of the measure. Make sure your shape is down, and then whatever shape you want to move, you rotate around that angle. Now, if you're using tracing paper, here's the thing though. I recommend, so when I do it, I put a pencil or something kind of like a pin or something to kind of hold the tracing paper in place at the center, at the turn center. And that will allow you to twist everything around so you can kind of see how it has twisted. Okay. And you'll notice it's easier to twist the thing that's on the top. So if you have like your tracing paper or your patty paper on top, you can twist that around by putting your pencil on top of the point and twisting by that angle. Okay. And I guess there's one more thing that I want to say about that. If you're using kind of patty paper to do this and you have like an angle, something like this, and what you're trying to do is maybe rotate this direction, you're gonna have basically a line that you're looking to twist. And so what you want to do is when you have your let's say here, your tracing paper on top, here's what I do. I put a dot on my tracing paper and I put a line right on top of this line. And that way, when I twist until my red line matches up with this other blue line. And that way I can see, did I move it the exact amount? If that makes sense. So I don't need to copy the whole angle. I really just need the center point and that segment, and then I twist until the red line lies on top of the other. So that's how I go about doing it when I'm doing it with the patty paper. All right. Let's see here. So that's a rotation, constructing a rotation. And it says to construct a rotation, then go ahead and do this. Now, if you let me go through. Woo! Let me do just a tiny little bit here. So what we're going to do is we're going to do a 125-degree clockwise, counterclockwise rotation with center O. So if you're doing this and you do not have tracing paper and you do not have, like, all you have is your little protractor, then, and let me get rid of figure 12, then here's what you want to do. This is kind of guiding you, or at least I hope it's guiding you through kind of your steps. So measure from O to A, create that little segment, then use your protractor because I'm going counterclockwise, right? So clockwise would be this direction. So I want to go the other direction. Okay. And I want to go 125 degrees. Now 90 degree would be about here. So I need about 30 degrees more than that. So right about in here, something like this. So I measure this out. Okay. And I use my, like a straight edge just to draw that line. Now take your compass and put your pokey part at O, turn at A, and then turn down here, and you'll see where does A prime go. Then you repeat the process. I'll use green on this next one. And I draw again a line from B to O. That's my starting point. Okay. And then once again, I measure the 125 degrees, wherever that gets me, somewhere over in here. And then I can kind of say, here's 125. And then I measure with my compass to see, because your compass will turn an arc. And you say, what is that arc? Make sure you're centered, pokey part at O, always for these. And you turn that and you're like, oh, okay, here's B prime right there. And then you repeat once again with C. And that's how you'll have ABC coming off in the correct direction. Okay. I'm going to show in a little bit how to use GeoGebra to do it. But again, if it's sitting there and it's on paper already, we don't have that same luxury, but we can do it. So to me, I like the compass approach. Now all of a sudden they're allowing you to use the ruler, which is fine, to be honest. If you have younger students, it's probably easier to use the ruler than it is to use the compass, and a lot less accidental poking and blood. So notice what they're doing then if they're using the ruler, which is fine. Measure your angle with the protractor and then mark that distance. Then once again, go back and repeat the same process. So they just kind of say, draw this, turn the angle, mark it. Okay. So rotation is an isometry. Again, isometry means same measure, which means under a rotation, the figure is congruent to itself. The image and pre-image are congruent. You could demonstrate this by side, 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 because all the sides have to be exactly the same. Okay. So the image of a line is a line. The image of a circle is a circle. The image of parallel lines is parallel lines. All of those are still holding true. And now we get a couple pieces here where you get to practice find the image under the rotation shown. Notice the rotation that is shown, right? The rotation that is shown is here. It's centered at O. So it's not about how many points I moved. It is physically about rotating a shape, this 90-degree angle. Personally, I like starting on some nice ones. So B is right here. So notice I would kind of say, here's B, rotating at 90 degrees. It is 2 units away. It's going to end 2 units away. Here's B prime. Okay. Next up is C, which if you look is up 3 and over 1. But when I rotate 90 degrees, it's going to be up 1, 2, 3 and right 1. So there's C prime. And likewise, A is over 1, up 1. When I rotate, it's going to be up 1, over 1. So here's A prime. And what I end up with is this triangle with the exact same dimensions that I had before, just rotated this direction. Very cool. Again, whenever I say very cool, I'm always like, yeah, I wonder, I don't know. Do they think it's very cool? I think it's very cool, but yeah. Rotations on a Cartesian system, that's fine. Um, again, you have a point, you rotate. So you'll see some where it's asking you to kind of sketch things. Again, just kind of picture what's happening, rotate it that distance around. Always okay to say, especially for a half turn or 180 degrees, those are nice ones, right? So it's okay to say, hey, those are going to be on a straight line, right? So however far away this one is right here, it's going to have to be, the image is going to have to be that same distance away down there. So there's your similarities. Yeah. And they talk about turn symmetries. We already saw these back in chapter 11. So they're kind of bringing it back, but saying, hey, take a look. If I was to rotate 72 degrees on this figure, it would sit right on top of itself. So that's how we can kind of see a turn symmetry. But also twisting things is not it's not a super bad thing. All right. Next up, for those of you who love art, tessellations. This is a tiling. We will do an activity with this in class on probably the next day of class. And the idea is going to be we're going to take out some shapes, physical shapes. They're kind of like Legos almost. They're not exactly, but and we're going to kind of put them together and see what kind of shapes we can form, what kind of shapes can we build. And a lot of these shapes are going to actually fill the plane. And when it fills the plane, we call it a tessellation. And one of my favorite artists, M.C. Escher, he did a lot with these shapes. And what he did is he kind of can show, hey, I can create a shape that will tile the plane and it looks really weird and really cool. And this is one that involved lizards. But basically, if you haven't seen these, he actually has some puzzles like this as well, where you basically, the puzzle pieces all fit together and you can just rearrange the colors as you see it. Okay. So in this tessellation, there are some things that you may or may not see. I'm going to try to point them out to you. Let me see if I can zoom in just a little bit more, because I think this is where occasionally art and math, well, they link up. And so I'm going to try a bright color because on this image, it'll be a little bit easier to see. So do you see right here how these shapes are all coming together at a single point, right? Yep. So in a sense, you can kind of say, ooh, maybe that's kind of like a triangle. Yeah, you wouldn't be too far off from that. Escher tends to do a lot of a lot of things that involve uh, things like triangles. But he also does things that involve, so I'm going to try to put these together, and you might see a shape that looks a little bit more like a hexagon. But when you have shapes coming together like triangles, right? So let's see here. If I put the heads together, then I get that. If I put the bodies together, 1, 2, 3, 4, 5, 6. So you get something that kind of looks like this shape right here. And so that shape, if you think about kind of cutting that shape out or turning it in, that seems like that's also could be the shape that he's using here to kind of create this illusion, if you will. So it says at the heart we see a regular hexagon. Yeah, maybe. I still kind of think it looks more like triangles. However, the regular hexagon, I guess I should show this briefly. The regular hexagon, when you see a regular hexagon, and it looks something like this, right? What's interesting is if it is a regular hexagon, what it's made up of is 6 regular triangles. So again, those two are kind of really tightly connected as we do it. But let's move on. Where do you see tessellations? Probably on the floor at a restaurant because they tend to lay out tiles in kind of a nice square pattern. You might see them offset a little bit, maybe with a brick wall. Bricks are offset just a little bit, but it's still tiles because it fills in all the spaces. Oops, now I'm too far in. So we're going to try to do something like this one in class together, but it's about creating tessellations with translations. And so any polygon that tessellates the plane, like a rectangle, draw any shape, blah, 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 cut this shape and do some work to it. So what they're doing here, what they're trying to show you is you can take one side, do a weird image here, right? And then push that, translate it to the other side. And it's guaranteed that this little piece here will fit in over here because it's an isometry. So when you start thinking of cutting the pieces out, this is one way to kind of think of it. Okay. Let's go down here, creating tessellations with rotations. So if you took a triangle and you did a little cut in from point B to the midpoint, then did a rotation around the midpoint, so it's jotting out, then these two shapes will fit together perfectly. Okay, like a key and a lock. And you can continue using that to tessellate the plane. Now I'm going to go ahead and show a couple as well with GeoGebra. And it talks here about which regular polygons tessellate the plane. And I mean, that's cool and all. We'll probably do an activity with this. And this is one. Oh, this is a cool one. I believe Marjorie Rice, who they thought they had found all irregular pentagons that tessellate the plane, and she found another one after reading an article in Scientific American by Martin Gardner. Now, Marjorie Rice was from San Diego, I believe. Let's see here. Marjorie Rice, Pentagon. Let's see here. Marjorie Rice, an amateur mathematician. Look at her. Look how happy she is. There she is. Yes, San Diego, California. Oh, so yeah. So she looked at things and she was like, I don't know. She just started trying them out. And it was kind of interesting because there were some mathematicians saying, yeah, I think we got them all. I think we got them all. She's like, maybe we don't. And so this is known as her secret pentagons. And this is, if you actually look at this, what's really cool, these are not regular tessellations. Go, Marjorie. Um, how many ads are we gonna have on this page? Nautilus. Okay, so I'm gonna zoom in a little bit here to show. This is 2 of the 4 tessellating pentagons that Rice discovered alongside artwork she created from the tessellations. So what you can see is that what we're talking about tessellation is it has to be the same shape. And so this is, if you look at it, 1, 2, 3, 4, and a little tiny tail there, 5. So it is a pentagon. It's definitely not a regular pentagon. But this shape, when she would reflect it over itself to make this piece here, right, then that shape would fit perfectly next to it here. And so she created a way to tile the plane with these tiles. And as you can see, the short stubby end always barters up with a short stubby end on the other side. But you don't just keep doing these kind of like that shape. You see these two come together, but then it goes off in another direction to fill the rest of the space. Very cool. Very, very cool. Over here, she has another one, and you'll notice, again, it is a pentagon. And you can see the reflection over itself to this other shape right here. And so if you look, you'll notice a lot of things that look like this. So there's one here. I'll do another one in blue right above it. And so you can see here it is again. It's the same shape. And so there's another one of them that fits right in there perfect. And so the angles that she had chosen come together so that you can actually see, here's another one of them. And they will always they'll always fill every space possible, which to me, I think is like, that is awesome. I love that that's what's cool about math, right? Some other things you don't have this, but here she's just sitting down and she sent it. She sent it in. She sent her work to Martin Gardner. Martin Gardner sent it over to a mathematician, a tiling expert at a college in Pennsylvania. But she didn't tell anyone. Yeah. She never told anyone because she didn't want to get in trouble with her dad. How about that, huh? She's busy creating mathematics and she does this. So we'll take a look at tessellating with other shapes and we'll kind of see how that looks. Here's a lot of irregular ones. Let's see here. Regular polygons are the big one. And yeah, let's see here. And that's it. I guess that's it. Woo! We did it. I said I'd show you some GeoGebra. So let me jump in here, geogebra.org. Let's jump into the geometry calculator and just kind of show just a little bit, right? What are we talking about? Well, let's take a segment like this. And we were just going to make any, this is any triangle. So I don't want you to make like a right triangle or anything like that. But notice, because they're blue, I can move any of these pieces, right? Okay, so watch this. I'm going to go down. I'm going to go to the ones that say transform. So when I transform something, that's different than perpendiculars and all that stuff. So notice, what do I have? I have translate. That's the slide. I have rotate. Okay, I can do that. And I can reflect. So what I'm going to do is I'm going to find the midpoint of this line right here. See that? And I am going to rotate the entire shape around the point. Now, I have to rotate an entire shape. So let's see if I can select objects. Here we go. I'm going to select all these objects. Okay. And then I'm going to rotate them around the point. Okay. And then it says how far. Well, if I do 45 degrees, I'll get this shape. Okay. I don't want that shape. So I got to go back up and select again. So I'm going to select again, but this time I'm going to rotate around that point by 180 degrees. Click, point, 180. And it doesn't matter whether I go clockwise or counterclockwise, because on 180 will get me right there. Now the reason why, oops, I must have had point selected. Did not mean to have point selected. The reason why I chose this is that, as you see, here's I have A, B, and C, right? I can move these points, any of these points, and it creates this. But I've also created a parallelogram, right? That's two congruent triangles. And if I have opposite sides that are the same in a quadrilateral, it's a parallelogram. So I know I've created a parallelogram. And what I'm going to do now is I'm going to demonstrate for you how we can actually do more with the transforming. So I'm going to I'm going to select objects. I'm going to select all of this. And now I'm going to transform by a vector. And it says select object. Okay, got it. Then vector. There we go. So what I did is I clicked a point and then another point, and that showed it how to move. Okay. And now I think I want to do that again. So I'm going to select objects, select everything, and then I'm going to go down and I'm going to find the transform, and I'm going to translate by a vector. This time I'm going to slide it to the right, and there it is. So what I'm creating is that tessellation, right? And so as I go, I could do it again. I'm going to select again. Which way? Maybe this time I'll go down. Okay. So this time I'm going to translate by a vector from here to there. It translates down. Okay. So and you can see I could continue doing this and it would fill the whole plane. The reason I asked you to not put any pieces in there is you can actually grab the original triangle that you had, and I'll make a polygon out of that. Doop, 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 doop. There we are. So you can kind of see where it was, but watch this. As I move any point, you can see how it will stretch in exactly the way that I'm showing, but every time it will fill the entire plane if I kept doing this over and over again, translating. So to me, that's pretty cool. And this is where you can make those Escher type pieces. If I cut this out, if I did some kind of drawing along in here and I rotated it around, it would make a different looking shape. So let me demonstrate that for you, because I think some of you will be very interested in this. So I'm going to save this one as any triangle tessellation. Okay. Let's see here. Let's go up and clear everything. All right. So what I'm going to do is I'm going to make my triangle like you would have normally done, just like we did before. But now I'm going to make it kind of a funky triangle because funky is awesome. So here's what I'm going to do. First, I'm going to have it tell me where the midpoint is. See this midpoint right here. There it is, right? And now watch. I'm going to hide that line segment temporarily. And here's what I'm going to plan on doing. I'm going to create some weird and funky looking stuff. See this? All this stuff, right? Zigzags like that. Okay. Now, this is where it gets kind of fun. I'm going to select all of that and that as well. So now I have all of this selected. Now come down and do your rotate around point D, right? I did that, right? Rotation around point. Select object. Now I want to select all the objects. Okay. I had them all selected. Come on. Select all the objects. Can I do that? There we go. That's fine. Oops, I got to make sure G is in there. There we go. Okay. And now if I come down to rotate around a point, I click the point and I say I want to rotate 180 degrees. Now watch this. It fills it in. Do you see that? Like it filled it in. You're like, what? No, that is awesome. So now here we go. So now as you do this, you don't have a triangle anymore, right? You have some funky, funky shape that doesn't look like, how could that possibly do anything I want it to do? Well, if you choose to select all of the objects and rotate through that center point one more time, 180 degrees, watch this, rotate around the point D, because that's my center point, and I'll rotate 180 degrees. You now once again have an outer parallelogram. It's just the inside gets all kind of funky. And because I rearranged it in whatever way I saw fit, you could actually create, by moving these around, create something where you're like, ooh, it looks like maybe if I made this really long and this one came back up here, right? You could make some kind of creature out of this. And you're like, oh, it looks like a blank. Maybe this looks like a bat wing or something. See how it's kind of flying in like that? Yeah. So you get to be in charge. You get to be kind of artsy, however you choose. Anyway, so yes, you can do that. And then all I do is copy this and I shift it up and it creates another one. If you wanted to, you could, and you have to be a little bit careful because you can't have them kind of integrated on themselves. Oh my gosh. Okay, that is cool, right? That's pretty cool. So you could do something else to another side. You could have done something else to another side, found the midpoint, done a rotational piece there too, and that would be perfectly fine. So keep in mind, you can actually take, I don't know, I think you can have a lot of fun with this one, with this kind of activity, because you get to be in charge and you could add more points along the way too, and you can make it more detailed, however you choose. Okay. So that's kind of a fun thing. I'll save this one and I'll save online. And this is Escher like with one funky side triangle. Okay. All right, let's clear it out. We'll try one more because I want to show you a couple things because I think this is super cool. Here, what we're going to do now. I want you to take and I want you to build, and you're like, okay, I'm building. Whoopity-doo. And I want you to build me a quadrilateral. Okay. So here's a quadrilateral. Yes. And what I can do is I can find the midpoint and I can rotate this entire shape around the midpoint. And I know you're like, oh, okay, very cool, 180 degrees. All right. Now take a look at what shape I've made. So now again, I can move the original side. So you might be thinking, oh, it looked like a trapezoid. It doesn't have to be a trapezoid. Okay. Okay. So here we go. Ooh, ooh, ooh. Right. Now what's great is as I continue with this shape, and I'm going to zoom out a little bit, I'm going to now select everything and I'm going to try to slide it. Oh, I want this to go perfect. So I'm going to translate, watch this, from this point to point D. And what you'll see is, I hope you can see, is that I now have, I want to hide that. Can I hide that? There we go. Okay. I now have created it so this angle matches perfectly. I can then copy again and it will fill in the gaps, which is pretty cool. So let's do that again. Select all objects and come down and translate by a vector. This time I'm going to go from point C. Point C, which became in here, right, is kind of where this piece wedges up. Well, that piece is wedged up here. So I need to go from C to B. Boom. And I am now, and you can kind of see it now, or at least I really hope you can see it now. I am tessellating the plane by, and I'm going to hide my other vector just so you don't see it here. And I can actually go back to the original. I can move this around to create whatever kind of funky shapes I want. I could create custom tiles. I could create custom bricks for my house that are my own special bricks. Womp, womp, womp. Okay. Now, if you're like, but hey, that doesn't look like it tiles, Scott. You're right. It doesn't look like it tiles. I should select all the objects and then translate once again, making sure that it's going to fill into one of those voids. So I'm going to go here to there. Boom. Right? And you're like, okay, I see it. I'll click Control A, which is selecting everything, and then I will translate again. And I want this point to go right into that little hole right there. Oops, I'm going the wrong direction. I guess that'll still work. There we are. Why did it not translate? Dork. Okay, hold on. I gotta hide my other vector. I'm getting too excited. Gotta hide that. There we go. Okay. Select all the objects. There we go. Translate by a vector. Okay, select my vector. I'm going to go from P over here to F. Boom. Boom. Oh yeah. Now, again, I'm going to hide that little arrow because the arrow is just showing that I'm just making a whole bunch of copies, right? But look at this, right? And I wonder if I can do select objects. Let me get rid of the labels. The labels are getting kind of, I think that's the issue, right? No, select objects and get rid of all the labels. Hide labels. I swear. I should have hidden the labels on the first one I did. Remember that if you're doing this on GeoGebra, hide the labels on the first one you do. So that way you don't have this the same issue I'm having. But anyway, just because the labels are there doesn't mean it's any more or less cool. So just hide them. And what I think is really cool is when you look at this, yes, you can definitely see that if you had given if your original shape was like kind of a rectangle, then you get kind of a rectangle shape back. But the reason why I really like this activity is that you can actually say, well, Scott, what if my shape was concave? And what you notice is it's still 100% tiles the plane, even though it's kind of this weird Star Trek logo looking concave piece. That shape, you could use that shape to completely tile the entire plane. So a lot of options, a lot of things you could do with this. Um, I think a lot of fun and cool things, especially with kids, because kids could then kind of make their own block, their own brick. And if you're wondering why is that the case, well, just think the angles inside of here have to add up to what number? 360 degrees. I know. So 360 degrees. So when you look at this, where this point comes together, you have one of every angle. Let me grab my writing tool here real quick. So okay, so obviously I have this angle, right? Then if I come down and look, I'm like, well, I have an angle like this. You're like, yeah, but it was rotated around this point. So this angle becomes that angle right there. Why? Because I rotated it. So the angles have to stay the same. Okay, that's fine then. What about this angle? Well, I've shifted everything over. So this angle is the same as that angle. You're like, well, really? Yeah. And this angle turns out to be the same as this angle. You could think of it rotating through the midpoint here if you wanted to. So I have a red, a blue, a green, and an orange, and they have to add up to 360. And that means I guarantee that it's going to tessellate. It's going to tessellate or tile the plane. Quadrilateral Tessellation. Boom shakalaka. Anyway, so there you go. So to me, again, that's kind of the really cool thing. If you wanted to explore more, you could start with something else that tiles the plane, like a regular hexagon, and then like take your regular hexagon, but then what you're creating is some kind of funky pieces so that when you map it together, you can you can you can do some fun things. If you were to, could you do some funky things with the quadrilateral? And the answer is yes. You could have started with a quadrilateral and done some funky things on one side, then did your rotation, right? And as long as you do funky things on that side, you can, oops, I was using the drawing tool here and not the move tool. As long as you do them on one of those sides, then it will absolutely match up as you continue going. So to me, you're creating kind of your own little piece of art, and you get to do what you want with it. So let's see here. Gotta go back to my original. There we go. Again, this one looks more like a triangle, right? But it didn't have to be a triangle. All right, so what do I mean by art? Let's just see here. So if you printed this out, obviously you would have hidden the labels, but if you would have printed this out, what could you do with it? You could come back here and say, okay, Scott, I'm going to do some art. So you're going to make this shape into, let's say here. So maybe this is a frog. Oh, that almost looks like a weird frog. Let me show you what I'm seeing, and then maybe again, not an art person, right? But I'm gonna make this polygon right here, and maybe you'll be able to see it when I do that. Okay, so there's this, right? And I'm gonna right click, I'm gonna go settings, color. I think I want to go kind of greenish. Maybe darker green, even darker. There we go. Okay, so now I've changed the color, and let me get rid of that for a moment. And the reason is then I can come in here and I could say, okay, I want you to see this, but I want you to see that this weird shape uh has like eyes and right, and then a mouth. I'll use red for the mouth, right? And so you have this. This is a like a frog. Right? Of course, it's a blue-eyed frog, which are very common in nature. And this frog's, "Rah!" And then if you look, when you rotate that around, it'll be like a frog kind of eating, and you'll have this other frog right here, and you'll have another frog. So you can actually make it um, whatever you want. So I hope you have some fun with that. Yeah, I'll probably throw an extra credit activity out there about that because I think that's I think that's pretty cool. All right. Hope that helps get you through. And I don't know, maybe you're curious about something now. Off you go.